let's take a look at some properties of sequences. We're going to start with a couple definitions. A sequence is bounded above if there's a number bigger than all of the terms of the sequence. And a sequence is bounded below if there's a number smaller than all of the terms of the sequence. We call a sequence a bounded sequence, or we can just say bounded, if it's bounded from both above and below. So let's look at an example. Consider the sequence 1 over n. Notice here that the starting and ending point have been left off. We're just going to assume that it goes from 1 to infinity. Notice that if I put in any integer for n, I'm always going to get another number smaller than 1. So the sequence is bounded above by 1. And 1 over n, if I plug in any number at all, but any integer, specifically for n, I'm going to get something bigger than 0. So the sequence is bounded from below. And here we can see a graph of this. Here are the ANs, A1, A2, A3, A4, and so on. That one should be A7. And I can see this dotted line is my bound from above, and I have another dotted line that is a bound from below. So 1 over n is a bounded sequence. Okay, now let's look at what happens if a sequence is not bounded. Suppose that I have a sequence an that's unbounded. Say it's unbounded from above. If that were to happen, then if I pick any number in the sequence, there must be some number in the sequence that's bigger than it, right? Because in order to be unbounded, no matter what number I pick, it's not big enough. So there has to be something later on that's bigger than it. So if I think of the values in the sequence, say on a graph, if you pick any number m, then there has to be some number that's bigger than it. Some number in the sequence. Maybe this is like A1000. But I could pick that A1000 as a new value of m. And since the sequence is unbounded, then, well, there has to be something bigger than this at some point later on. Okay, so the numbers have to keep getting bigger and bigger. That means that the sequence is going to diverge. Okay? Similarly, if it's unbounded from below, then the numbers have to be going, further and further down. So the sequence is going to diverge. So we have a theorem that we can state. If a sequence converges, then it is bounded. Okay, and what we're doing here is just saying the contrapositive of what we just discussed up here, right? So up here we said if it's not bounded, then the sequence diverges. Okay, logically speaking, that's equivalent to its contrapositive, right? So it's the conditional where we have both the converse and inverse, right? We swap the statements and negate the statements. Okay, so this means the same thing as saying if the sequence converges, then the sequence is bounded. Okay, so let me show you an example right away. Consider the sequence -1 to the n. Okay, so this sequence, when n is 1, I'll have -1. N is 2, -1 squared is +1. It's just going to be a negative for the odd numbers and a positive for the even numbers. Okay, so the sequence is bounded, right? It's bounded above by 1 and bounded below by -1, but it diverges. So we have to be careful about our statements here. Our theorem says that if a sequence converges, then it's bounded. That's not the same as saying if it's bounded, then it converges, because here I have a bounded sequence that diverges. So a bounded sequence may converge or it may diverge. We don't know. That we have to check on an individual basis. This theorem doesn't help us with a bounded sequence. What it's saying is if the sequence converges, then it must be bounded. All right, now let's talk more about these bounds and how things move around. We can say that a sequence is increasing if it's always going up. So just like with the graph of a function, if the values are always getting bigger, then it's increasing. If the values are always getting smaller, then it's decreasing. A monotone sequence is a way to say increasing or decreasing without specifying which one. It's just saying it's moving in one direction. It could be either one. It could be either increasing or decreasing. Now, we also want to be a little bit careful when we talk about a sequence. We don't really care that much about the first couple of terms. Okay, that's what this business here is saying, that if we call a sequence increasing, it may not be increasing for the first couple of terms, right? Maybe the first term is bigger it goes smaller, and then it starts getting bigger again. We still call this an increasing sequence. It just doesn't start increasing until n is 2, right? Or here, if I have a couple of terms where it's getting bigger and then smaller, this doesn't start decreasing until n is 3. We can still call it a decreasing sequence, right? So these are both monotone. All right. So if I look at this sequence, n minus 10 squared, and we ask, is it monotone? What I want to do is look at the first few terms. When I plug 1 in here, 1 minus 10 squared is negative 9 squared, or 81. Okay. When I plug 2 in, 2 minus 10 squared is negative 8, which squared is 64. When I plug in 3, I'll have 3 minus 10, so 7 squared. Sorry, negative 7 squared, right? And so on. So this one starts off looking like it's going down. So A8, when I plug in 8, 8 minus 10 is negative 2, squared gives me 4. A9, when I plug 9 in, subtract 1, I get negative 1, squared is 1. When I plug in 10, I'll get 0. When I plug in 11, 11 minus 10 is 1, squared gives me 1. And now it's going to start getting bigger. Okay, so if I consider for n greater than or equal to 10, it's always going to be getting bigger, right? For n greater than or equal to 10, right, something bigger than 10 minus 10 will give me, a positive number. And as the n gets bigger, I'm going to get a bigger positive number that gets squared. So for n bigger than 10, the sequence is increasing. So it is monotone. Right, we call it monotone increasing, or we can just say it's a monotone sequence. Okay, we have a little theorem here. Suppose that we have a sequence that's bounded and it's monotone, then it converges, right? So before we said that I could have a sequence that's bounded but doesn't converge, right? And I gave this example where it flips back and forth between 1 and negative 1. So this is a bounded sequence, but it's jumping around. A monotone sequence can't really jump around. It can only move in the same direction. It's either always increasing or it's always decreasing. And if it's bounded, then it can't get any bigger than a number, and it's going to keep getting closer and closer to that number. So it's kind of stuck to converging to that number. Kind of explaining this on a graph. Let's suppose that I have a sequence that's monotone increasing, and it's bounded. Okay, let's suppose that it's bounded above by, say, 10. Okay, and let's suppose that 10 is the smallest number that it's bounded by, right? If I pick anything smaller than that, that's not a bound. So then if I think about, what the ANs look like, they're always getting bigger, and they're getting closer and closer to that 10, and that's exactly what we mean by a limit, right? So that's the limit is 10, so it converges. Okay, so that's not really a proof. That just gives you kind of a rough explanation, but I think that that's going to be okay here. And that's, I think, all the extra stuff that we want to talk about for sequences.